Let me introduce myself. I'm Nicoletta Krachmalnicoff. I work here in Trieste at CISA, and mainly I work in the field of analysis and simulations for cosmic microwave background signal. In the past few years, I've started to dig a bit into machine learning, trying to understand whether there is the possibility to use machine learning in trying to tackle some of the problems that we have in the analysis of the cosmic microwave background. And I've been asked to give a talk about machine learning in cosmology here. So what I will try to do is to give an overview, very incomplete, of which are the application currently that people are trying to do with machine learning in cosmology. So it's not going to be complete. Let me start with this, just to give you a few numbers. So this is a plot that usually I show at lectures when I give lectures about neural networks at CISA, just to give you an idea of the number of papers that are being published in astrophysics in the recent year, having in the abstract the words neural network compared to the word Bayesian. And you see that there is really a huge growth of paper trying to apply machine learning in cosmology. And in terms of total number, we are maybe already exceeding the number of paper explicitly using Bayesian statistics in astrophysics. So it's a bit hard to keep the pace with all these application of machine learning in cosmology. And it's also hard to understand. So as I will tell you also later, we are still in somehow an exploratory phase where we are trying to do many things with machine learning in cosmology. And it's still hard to understand what will remain at the end and what is just tests, which is still important, but will end in a dead path, let's say. Okay, so as you all know, and has been said already in the previous talks, so we have our standard model of cosmology, lambda CDM, which is working really well. The data are in good agreement with our theory, but of course there are a lot of open questions that we don't have answer yet to. So for example, nature of dark matter, nature of dark energy, what is the current theory of inflation, whether inflation really happened, which are the masses of neutrino, the tensions, and so on and so forth. And there are a lot of experiments that are now taking data or will start to take data in the future explicitly with the goal of trying to understand and to give answers to these questions. So as you all know, we have two main observables in cosmology, which are very different in nature. So one is the cosmic microwave background, the first radiation emitted by our universe. In this case, we are dealing with somehow a simple signal in the sense that it's fully Gaussian, almost perfectly Gaussian. So in principle, it should be easy to be analyzed. But at the same time, it's a very faint signal, especially when we deal with polarization. As I will tell you later, the polarized signal is extremely faint, so it's highly contaminated by other kind of signals which are complex and not Gaussian at all, like the emission from our own galaxy or the presence of non-idealities, so instrumental systematic effects. So this makes our life much more complex. On the other hand, we have the large-scale structures, so the galaxy surveys that probe the later evolution of the universe. And in this case, the signal is much more complex. So it involves highly nonlinear physical processes, and it's intrinsically more complex to be analyzed. So as I was saying, there are a lot of experiments which are starting to take data or are being built and will take data in the near future, probing both the CMB. This is the experiment I'm more familiar with because I'm highly involved in those, or galaxy surveys. And so in the near future, we will have a lot of new data that we need to be able to analyze in an efficient way. So now the question is, are we ready to fully exploit this data that will be available in the near future, given the amount of data, so really the huge amount of data that we have, the signal complexity we need to face, and the precision that we want to achieve? So probably the question is no. So there is still margin to improve our data analysis technique in order to be sure that we will take advantage of all the data that we will have in hands soon. And machine learning, of course, the answer is that machine learning in principle could help. So if you are an observational cosmology, you should be familiar with the standard way of analyzing data. So basically, the typical way is the classical way is to use Bayesian inference, so Bayesian statistics. And in order to do that, we basically need 3 ingredients. So we need our theory, and then we need simulations that cosmological simulation that incorporates our theory. Then what we usually do is to define and compute summary statistics of these simulations in order to compress the information into something simpler that we can deal with. And then once we have the summary statistics, we compare the summary statistics with the data, and we do inference. So we need to define a likelihood model, a analytical likelihood model, and then sampling the parameter space in order to then constrain the value of the cosmological parameters we are interested in. So these are the classical steps of data analysis in cosmology. And in principle, machine learning has the potential to help in all these steps in order to be more efficient or faster than traditional methods. I've highlighted here the word potential because, as I was saying before, we are even though we know that in principle machine learning could help in that, we are still in trying to explore whether at the end this is really doable. So now I'll just try to give you some examples on application of machine learning in these 3 steps of data analysis technique. And I will give some general example and then a couple of work I've done in the past related to the CMB science. So one thing is that is working really well is about the second step. So as I said, usually what we do in the standard way of analyzing data is that we define and we compute summary statistics. Typically, the typical thing that we do is that we compute power spectra, 2-point correlation function, or the Fourier transform of it, so the power spectra. And even though it's in principle simple to do that and to compute the summary, this kind of summary statistics from our data and from our simulation, we need to take into account that when we do inference, so we constrain the value of our cosmological parameters, we need to call and compute these summary statistics for a large parameter space, so we need to do it many times. And the typical way of doing that is by using, and to compute the summary statistics is by using Einstein-Boltzmann codes, so like, for example, Camden class. And when we do inference, we need to call them 10 to the 5, 10 to the 6 times in order to really sample the parameter space and reach convergence in our MCMC chains. So this could be computationally expensive, and machine learning has proved to be great in trying to make this step and this procedure faster. And in particular, by we can build emulators, so something codes that can compute and interpolate and compute the summary statistics in a much faster way than the standard codes. And these are based on usually on neural networks, so and pretty simple neural networks, so fully connected, few layers, shallow neural network, and so they are pretty easy to build and pretty easy also to train. So this is I mean, it's already proved to work really well and to also be applied to data. And here you see an example where I just taken from this paper here by Boris, and where I just compare they just compare the posterior distribution of the parameters obtained by Planck, so with the standard computation of power spectra for the CMB, and while using an emulator, so CosmoPower built on a neural network to compute the power spectra. And you see that the posteriors are in great agreement, and the difference is that with CosmoPowers you can really sample the parameter space in a fast way just by using a laptop in a few hours. While with Planck you need a with the Planck likelihood and sampling you need a supercomputer to do that. So this is one thing, just an example of something that is already working really well and it's already be applied in cosmology using machine learning and neural networks. The second thing, as was also said before, is inference. So basically, we could think about, and we are thinking about using machine learning to do inference, so to really constrain the value of the cosmological parameters. The advantage of that, as was said also before, is that in principle there is no need to define a summary statistic in this case. We know that even so for the CMB, the power spectra is a sufficient summary statistic because the CMB is Gaussian, but for the large scale structure, this is not true anymore. So whenever we do inference just by taking into account the 2-point correlation function, we are losing some information that is present in the data. So with machine learning, in principle, we don't need to do that, and we could just use the whole data set in order to do inference on one side. On the other side, there is also no need, in principle, of an analytical likelihood model to do inference, but you can train directly on simulations. And this is very useful, for example, for the CMB, as I will tell you later, because even though, as I said, the CMB in principle is simple because it's Gaussian, so the computation of power spectra should be enough. But at the same time, we have systematics, we have foreground residuals, and in most of the cases, we are able to simulate them, but we are not able to write down an analytical likelihood that model them. So for this reason, using machine learning to do inference has a great potential, both for large-scale structure and CMB. So there has been in the recent year many different implementation and tests on that, using different kind of neural network or other kind of machine learning experiment, machine learning algorithm. In this case here. And just the important thing is that most of them have been tested and applied only on simulation. So there is very few application on real data at the moment. And just here, I'm just highlighting one of the problems that we have for doing inference with machine learning for large-scale structure. One of the problems that we have is that at the moment, it's hard to marginalize over systematic effects, baryonic effects, and these can cause biases in our final estimation. There are ways to solve them, and there are people working on that. But this is one of the main problems that we have with inference with machine learning for large scale structure, and this is one of the reasons why the application on data are still lacking. We are not there yet. One thing that we did in the past month, together with Kevin Walls, a student at CISA working with me, and with Luca Pagano from the University of Ferrara, was to trying to do inference with neural networks on CMB data. And this is one of the first applications of convolutional neural network-based inference on real data in cosmology. So the goal here was to try to infer the value of one of the cosmological parameters, so that the optical depth to reionization, directly from Planck maps using neural network. The reason why we try to do that is there are two reasons basically. The first one is that tau is one of the cosmological parameters of the lambda CDM, which has the largest error. And the reason for that is because in order to constrain them, we need to use the CMB polarization data, E-modes polarization at the very large angular scales. And these very large angular scales are highly affected by systematic effects and foreground residuals. And these cannot be modeled analytically, as I was saying before. So writing down an analytical likelihood, it's complex. And in the second reason is because testing the inference with neural network on the tau parameter is instructive in order to arrive then to do that for B-mode, so for the tensor to scalar ratio, because both tau and R somehow impacts the large angular scale of the CMB, although tau is much easier because it affects the E-modes, which are much larger than the B-modes. So testing it on tau is an instructive test before going to B-modes in the future. So as I was saying, we use neural network to infer tau directly from Planck maps. We use the Planck raw resolution maps at 100 and 143 gigahertz that you see here. And here you see, as I was saying, that they are really impacted by spurious signals. So not only the galaxy, but also an intermediate and high galactic latitude, you see signals which are coming from the dipole, so from a leakage from total intensity to polarization. These residual, as I was saying, are highly non-Gaussian and are hard to be modeled analytically. And for this reason, the current constraint or tau are based on empirical likelihood. So a likelihood which is not analytical, but it's based on cross spectra, and it's obtained through simulations. So our goal is to avoid the computation of cross spectra and just use convolutional neural networks directly from map to infer the value of tau. In order to do that, we needed to use convolutional neural networks which are working on the sphere, which perform convolution on the sphere, because I mean, as I said, tau impacts a very large angular scale, super degree angular scale, so we cannot make any flat assumption, but we need to take into account the whole celestial sphere. The way we train our neural network is with two kinds of simulations. In the first step, we train the neural network with somehow simple simulation that contains only CMB plus Gaussian correlated noise. So with the Planck covariances, so the correct value of the noise, but without the inclusion of any non-Gaussian systematic effects, which we know that are present on the map. And then we made a more complex training by including also in the training the presence of these systematic effects. And here I just show the results in the first case. So when we train the neural network on something simpler, which is much more simpler than our data, only CMB and Gaussian noise. And we do that in two different cases. In one case, we input to the neural network only one channel, so only the 143 maps. And in the second case, we input also two channels to the neural network, so the 143 and the 100 gigahertz channels from Planck. What you see is that when you train your neural network on Gaussian simulation, and then you apply your neural network to Gaussian simulation, everything works well. These two plots here, everything is unbiased, so the neural network is able to infer the value of the cosmological parameter of tau. But whenever you apply this trained neural network on maps that include systematic effects, what you see is that when you have a single channel input, your neural network is really biased, as expected. These systematics are non-negligible. But when you've trained your neural network on having as input two channels, you arrive to something which is close to be unbiased. So when you train the neural network having two channels as input, the neural network has learned how to recognize the common cosmological signal and to neglect the presence of systematic effects. And it's doing that in a more efficient way than just taking the cross spectra of cosmological parameters. Okay. Oh, sorry, the cross spectra of the two channels. So we did that. We also, as I was saying, tested, train a neural network in a more complex way. So taking into account the presence of systematic effects on the maps. In this case, we were limited by the number of simulations. We only had 500 simulations, which is not a lot for training a neural network. So we had to come out with a procedure to do that. At the end, we managed to arrive to fully unbiased results. And when we arrive there, we apply our neural network to the data. So these are the constraints that we get. In green, you see the previous constraint coming from the cross-CL empirical likelihood compared with our two trained neural network, the Gaussian one in blue and the one containing the systematic effect. So the value on two different masks. The value of tau are in very good agreement with what you get from the standard way of inferring the value of tau, so from the cross spectra. We get somehow larger error bars whenever we include systematic effects. The message that I wanted to highlight here is that it took a lot for us to go from something that was working really well on simulations, but to arrive to something which was robust on data. So the step to go from something which is working on simulation to something which is really robust on data is a huge step. And so we need to take into account that when we talk about machine learning in cosmology, something that works on simulation is not guaranteed to work well on data. The last thing is that neural machine learning can help a lot in principle in doing simulations. So we need a lot of simulations in cosmology, and somehow usually these simulations are very computationally expensive. And there is an ongoing effort to use neural networks in order to try to arrive to something more efficient. For example, from going to dark matter simulation to fully hydrodynamical simulation using a neural network to do the job. Again, this seems to be working well, but not yet at the level of applying it to do inference and then to analyze our real world data. I'm running out of time, so I'll be quick on that. So we did another work trying to simulate with a neural network the foregrounds of our galaxy, so the galactic emission in the microwave sky that looks as a foreground for the CMB. The reason for do that because foregrounds are probably the main challenge that we have in the analysis of the CMB radiation, and we don't have good enough simulation yet. And in particular, we don't have a simulation of the non-Gaussian signal coming from foregrounds at the small angular scales. We have only few data on that, but we need to be able to simulate something because we need to test the impact on that on lensing reconstruction and then delensing. So we did that, and this is working surprisingly well. We did that with generative adversarial networks. So basically, we train network to go from low resolution maps to high resolution maps on those regions on the sky where we have some high resolution data. So from Planck at high frequency close to the galactic plane. And then once we were able to, the neural network is trained to do that, we apply this neural network to other regions of the sky or to polarization. This is working really well. Here you see an example. So this is the input of the neural network, the low resolution map. This is the real high resolution map, and this is the output of the neural network. And you see that they look great. Not only the power spectra are correct, but also the higher order statistics. So here you see the Minkowski functionals, and they look really similar. So the neural network is able to produce small scales which are non-Gaussian. We did that in total intensity. We did that in polarization. We go to 3 arc minutes. This is a work done by Jian Yao, another student worked with me at CISA. And at the end, we managed to get a full sky high resolution map at 3 arc minutes in polarization with non-Gaussian small scales. So, and soon we will try to understand which is the impact of this non-Gaussianity on the lensing reconstruction and then the lensing. That's it. Just my personal concluding remarks about the possible use of machine learning in cosmology. So of course, machine learning offers a lot of application with a potential of enhancing data analysis and make it more efficient and take advantage of it to really retain all the information which is present in our data. The field is still in exploratory phase. There are a lot of feasibility tests ongoing, but real world application on data are limited. Going from something which is working well on simulation to something which is working and robust on data is a huge step. So this is something that people need to take into account whenever we see paper working well on simulation. This is not a guarantee that it will work well on data at the end. And in my view, at the moment, machine learning, it appears to be a complementary tool. It's not yet revolutionary. Maybe it will be in the future, maybe not, but we don't know yet. And that's it. Thank you.